One of the reasons for drawing Lewis structures is to be able to analyze molecular shape. Molecules that have 3 or more atoms will come in many different shapes. Almost all of the shapes are three-dimensional, except for the few that lie in a plane or lie in a line. Shapes are all made from 5 basic geometrical structures. Shapes are classified according to the number of electron domains they contain around the central atom. An electron domain could equal a lone pair of electrons or a bonding atom around the central atom. The 5 basic shapes that all other molecular shapes that we learn that will be derived from include linear and trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. The simplest shape for a molecule with 3 atoms that we can have is linear. The representation would be for an AX2, where the letter A we use to represent the central atom, and the letter X we use to represent the outer atoms. In this scenario, we have 2 outer atoms surrounding our 1 central atom, and no lone pairs on the central atom. When this happens, the molecule will be linear, and the bond angles will be 180 degrees. The second major shape is trigonal planar. Trigonal planar molecules follow the format of AX3. We have A as our central atom and 3 outer atoms, which we're representing with X. And if we look at another view of the molecule, we can see that all 3 of our outer atoms and our central atom are all lying within the same plane. Therefore, it's a planar molecule. The bond angles for XAX are all 120 degrees apart. So we have 120 degrees right there. We have another 120 degrees here and another 120 degrees here. You can imagine a full circle being 360 degrees, and 360 divided by 3 would give us 120 degrees each. The third major shape is tetrahedral. The molecule form for tetrahedral is AX4. That means that we have 4 outer atoms surrounding our central atom, and the shape is similar to the geometric shape of a tetrahedron. So at the corners of a tetrahedron, that's where our X's would be in this molecular shape, and we would have our central atom somewhere in the middle there. The bond angles for a tetrahedral molecule are 109.5 degrees approximately. The fourth major shape is called trigonal bipyramidal. Molecules will have the format of AX5, 5 outer atoms surrounding the central inner atom. Trigonal bipyramidal is similar to taking 2 tetrahedrons and stacking them on top of one another. There's 2 different positions we can consider within the trigonal bipyramidal arrangement. The 2 groups that are sticking straight up and straight down are referred to as the axial positions, whereas the 3 other atoms lie within a plane similar to trigonal planar, and these are referred to as the equatorial positions. Therefore, we end up listing 2 different bond angles for the trigonal bipyramidal molecule, because whether we're referring to an equatorial to an axial position, those are going to be 90 degrees apart, versus an equatorial to another equatorial position, those are going to lie in a plane and be 120 degrees apart. So often the bond angles are listed by saying 90, 120. This image shows a little bit of a simplified trigonal bipyramidal structure, so you can see those axial positions, so 1 up and 1 down, and the 3 equatorial positions all lying within that trigonal planar plane. The final major shape is called octahedral. Molecules that are octahedral will have the format of AX6, or 6 outer atoms surrounding the central atom. It takes its name from the geometric shape of an octahedron. An octahedral molecule will have 90-degree bond angles for the XAX between any position within that molecule. And we can see that there's 4 of the atoms that will lie within a plane that take on kind of a square planar arrangement. And then we have two outer atoms that live above and below the ones that are within the plane. The following shows a summary chart between the 5 major geometric shapes. We had 2 domains around our central atom when we had a linear molecule. Domains can either be lone pairs or atoms bonded to the central atom. So far, we haven't looked at any of the examples where there's lone pairs on the central atom. When we had 2 domains, we had a linear shaped molecule. When we had 3 domains, our major shape was planar triangular. When we had 4 electron domains, our shape was tetrahedral. 5 electron domains, the shape was trigonal bipyramidal. And 6 electron domains, our shape was octahedral. We're going to learn more shapes that fall within these families, but they will always take the shape from the major one that they're within the family of. Next, we are going to go through a handout, which is a blank chart where we're going to build up our molecular structure through a concept known as VSEPR theory. VSEPR stands for valence shell electron pair repulsion. This theory is useful for predicting different molecular shapes. Electron clouds or domains are a space that is occupied by a group of electrons. A group of electrons could be a bonding domain. It could be either a single, double, or triple bond. Either one of those would still just equal one domain. Or we could have non-bonding domains. One non-bonding domain would be one lone pair of electrons on that central atom. VSEPR theory comes about because electrons are negative, and electrons that are too close to each other are going to have repulsions with one another. Therefore, the molecular shapes are formed because the electrons want to spread out as far as they possibly can, and the different amounts of domains that are around the central atom will dictate how many shapes we can form. There is a blank chart within the handout section of Blackboard that matches the chart that we're going to fill out together here. You also might have this in your notes packet as well. It would be useful to print off this blank page and follow along filling out this chart. In order to determine the shape according to VSEPR theory, the first thing we have to do is draw a correct Lewis structure and then determine the number of electron domains, sometimes called electron clouds, that surround the central atom. After that, we'll assign what's called a VSEPR class. Then we can determine the major electron geometry. This will come from one of those 5 classes that we saw earlier. Then we can determine the molecular geometry, which is more like the true shape of the molecule. Once we know what the true shape is, we can say what the bond angles will be. So starting with BeCl2, if we draw our Lewis structure for this molecule, we would end up with something like this. And recall that beryllium is one of the few that forms an incomplete octet, so it's happy with only 2 bonds, which are 4 electrons around it. The number of electron domains in this example is going to be 2, because we have 1 outer atom here and 1 outer atom here. So a total of 2 electron domains. Our VSEPR class would be an AX2 type molecule, A representing the central atom, X representing the 2 outer atoms. And for VSEPR class, we use a method known as the AX or AXE method, where A is the central atom, X is the outer atoms, and E is any lone pairs on the central atom. Our electron geometry for AX2 is linear. And in this family, the only one there is the first one, where there's no lone pairs on that central atom, the true shape is also linear. Our bond angles we saw between our 2 chlorines and our beryllium are going to all be 180 degrees apart. So for a linear shape, the bond angles will always be 180 degrees. Moving on to the next one in our family, BH3. If we draw our Lewis structure for BH3, we're going to have one central atom and 3 outer atoms, which are all hydrogen. The number of electron domains, we have 3 bonding domains because we just have 3 atoms surrounding the central atom. So we're going to have 3 for our electron domains here. Our VSEPR class would be AX3. Our electron geometry is going to be trigonal, planar, so this molecule is flat. And for the first one in every given family, where they all have the same number of electron domains, the molecular geometry will be the exact same as the electron geometry. So the actual shape of BH3 is also called trigonal planar. The bond angles between boron and 2 hydrogens are 120 degrees apart for a trigonal planar molecule. So 120 degrees for our bond angles. Now our next example, SO2, what's going to happen if we still have 3 electron domains around the central atom, but we replace one of our bonding domains with a lone pair or a non-bonding domain? So this is going to fall within the same family, but our shape is going to be a little bit different and our bond angles are going to be a little bit different. First, we need to draw our Lewis structure for SO2. We're going to have sulfur as our central atom. We have our 2 oxygens on the outside, and we would end up with 1 double bond to our sulfur, oxygen. We'd have 1 single bond to our sulfur, oxygen, 2 lone pairs on the outer oxygen, and then 3 lone pairs on the other outer oxygen. But we would also be left with 1 lone pair of electrons on the central sulfur atom. When we're counting up our electron domains, we count 1 for our first oxygen, 2 for our second oxygen, and 3 for that lone pair of electrons on the central atom. Therefore, we still have 3 domains. Our VSEPR class is going to be AX2 E1, or just E. The E represents that lone pair of electrons on the central atom. We know the electron geometry is trigonal planar, but when we consider the shape, you can take your hand and cover up that lone pair of electrons and think, what would the shape actually look like when we don't take any lone pairs into account? And the name of the shape for an AX2E molecule is called bent. The bond angles are going to be close to the bond angles for the family, which is 120 degrees. But when you replace a bonding pair with a lone pair of electrons, that lone pair occupies a greater amount of space than a bonding pair because those electrons are free and not tied up in a covalent bond. So they end up pushing down on the outer atoms by a little bit, and therefore our bond angles become slightly less than 120 degrees. We don't have to know what the exact bond angles are. The bond angles will change depending upon what the real molecule is. We just want a general trend here. So when we have a bent shape, that's AX2E, we can say our bond angles are slightly less than 120. That will be true for any time we're in a given family and we replace one of the bonding domains with a non-bonding domain. The bond angles will always shrink slightly. Continuing along with building up our shape chart, we now have CH4 as our example. So first we would draw a Lewis structure. So we're going to have carbon singly bonded to 4 hydrogen atoms. And our number of domains, or electron clouds in this case, we have 4 bonding domains around our central atom. So now we're in a new family where everything has 4 domains. Our VSEPR class would be AX4. And everyone in this family is going to have the same electron geometry, which is called tetrahedral. And the first one within the family, which is our CH4 or methane example, the molecular geometry, which is the true molecular shape, will have the same name as the electron geometry. So methane's shape is called tetrahedral. The bond angles for a tetrahedral molecule, it's hard to see because this is a 3D shape and we're writing it on 2D paper, but it's 109.5 degrees apart, because they lie in the corners of that tetrahedron shape. So 109.5 degree bond angles. When we move to the next one within the tetrahedral family, NH3 is a good example. If we draw our structure for ammonia, we're going to have 3 outer hydrogen atoms, and we're going to have 1 lone pair of electrons on our central atom. We still have 4 domains, 1, 2, 3 bonding domains, and 1 non-bonding domain, so the total is 4. Our VSEPR class we would represent as AX3E1 or AX3E. The actual shape when we have 1 bonding domain replaced with 1 non-bonding domain within the tetrahedral family is called trigonal pyramidal, because that's kind of the shape you see when you actually cover up that lone pair of electrons. It looks like a pyramid and there's 3 outer atoms. The bond angles between nitrogen and 2 hydrogens are going to be slightly less than 109.5 degrees because now we have that lone pair of electrons pushing down on our bonding domains. For ammonia, the bond angles are about 107 degrees for this molecule, but what we really need to know is that they're slightly less than 109.5. Our next example is H2O or water. Let's draw our Lewis structure first. We have oxygen in our central position, and on our oxygen atom, we're going to have 2 lone pairs of electrons. So 1 domain here, 1 domain here. Our total number of domains is going to be 4. We have 2 bonding domains and 2 non-bonding domains. So we're still within that major tetrahedral family for the electron geometry. How we would write the VSEPR class is we would have AX2 because we have 2 bonding domains, and then we say E2 for the 2 non-bonding domains now. The actual shape of the molecule or the geometry when we have AX2E2 is called bent. This is the second shape that has the same name. We saw that earlier with the AX2E molecule, but they both are just called bent. Our bond angles are still going to be slightly less than 109.5 degrees, but now they're going to be even less than the last example. So the HOH bond angles for water are 104.5 degrees. Now we've replaced 2 bonding domains with 2 non-bonding domains, so the 2 lone pairs on oxygen are pushing down even more so on the oxygen-hydrogen bond angles, shrinking them even more. So we're less than 109.5 degrees, and for water, they are 104.5 degree bond angles. That wraps up the tetrahedral family on the last slide. Now moving into the next family, we're going to have PCl5 as our first example. So drawing our Lewis structure, we'll have phosphorus as our central atom. Phosphorus can have an expanded octet because it's in the 3rd row or lower of the periodic table. And we're going to have 5 chlorine atoms surrounding our central phosphorus atom. Each chlorine will have a complete octet. We don't care about the lone pairs on the outer atoms. We only care about if there's lone pairs on the central atom when we're determining the shape. So here we have 5 electron domains or electron clouds around our central atom. They're all bonding domains. So we've got 1, 2, 3, 4, 5. The VSEPR class is going to be AX5. And the electron geometry for the AX5 family is called trigonal bipyramidal. The molecular geometry or shape for our PCl5 molecule is also called trigonal bipyramidal since it's the first one in the family. And the bond angles, as we saw in our 3D structure before we started filling out our chart together, we list two bond angles. We list an equatorial position to an axial position is 90 degrees versus equatorial to equatorial positions were 120 degrees apart. So the bond angle between phosphorus and these two chlorines would be 120 degrees, whereas the bond angle between that axial chlorine and the equatorial one would be 90 degrees apart. The next one in the family we can draw is SF4 for an example. Let's draw the Lewis structure for SF4. Sulfur will be our central atom. We're going to place two of the fluorines in the axial positions, complete their outer octets, and the other two fluorines will end up in the equatorial positions. One of the atoms that was within the equatorial position for the AX5 molecule will be replaced with a lone pair of electrons. This is the most stable position for a lone pair of electrons because equatorial positions within the equator are lower in energy than the two axial positions sticking straight up and straight down. Therefore, when we start replacing bonding domains with non-bonding domains, we'll take them away from the equatorial position one at a time. Our number of electron domains for SF4 is going to be 1, 2, 3, 4, and then 1 non-bonding, so a total of 5. We're still within that same family, so still 5 domains. The VSEPR class would be AX4E or AX4E1 because we have 1 non-bonding domain. And the actual shape for our molecule is called seesaw. If you were to imagine turning that shape on its side, you could see that it kind of resembles a teeter-totter or a seesaw, and that's where the name of the shape comes from. And if you recall, we just said when we replace one of our bonding domains with a non-bonding domain, it shrinks our bond angles a little bit, and so our bond angles are going to be slightly less than the standard 90-120 degrees. So we could measure our bond angle between an axial fluorine atom and an equatorial fluorine atom, and that would be slightly less than 90 degrees. And then the bond angle between two of the equatorial fluorine atoms would be slightly less than 120 degrees. Next one within the family we can draw is ClF3 as an example molecule. So chlorine is going to be our central atom. There's only one of it, and we're going to be surrounded by 3 fluorine atoms. So we're going to have our 2 axial fluorine atoms, and now we're going to be down to having 1 equatorial fluorine atom. Complete the octets on the outer fluorine atoms. So each of them have 3 lone pairs. And on our central chlorine atom, we're going to have 2 non-bonding domains. So 1 lone pair here and 1 lone pair here. The lone pairs are in that equatorial position where we replace them, which is lower in energy, therefore more stable. Our number of electron domains, we've got 1 bonding, 2 bonding, 3 bonding. We've got 2 non-bonding domains now, so 5 electron domains. The way we represent the VSEPR class for any molecule that falls within this shape would be AX3E2. Still trigonal bipyramidal for the electron geometry. The true shape of the molecule, if we cover up the lone pairs on the central atom, is called T-shaped. Notice that if we just look at the fluorines around the central atom, they're in the shape of a T. That's where the name of this class comes from. The bond angles now we don't have 2 bond angles to list anymore. All we have is a bond angle between an axial and 1 equatorial fluorine left, and those are going to be slightly less than 90 degrees. There's no 2 equatorial positions that we can measure between anymore. So we only have to list that our bond angles are a little bit less than the perfect 90 degrees because of the 2 lone pairs within the molecule. Our next and last one within the 5 electron domain category, an example is XEF2. we're going to have xenon as a central atom. We would have a fluorine going up and a fluorine going down, both in the axial position. Complete the octets on the outer fluorine atoms. Now we're going to have 3 non-bonding domains that took up the equatorial positions of our trigonal bipyramidal shape. So we still have 5 domains total. Our VSEPR class is AX2 because we have 2 bonding domains, and then E3 because we have 3 lone pairs on the central atom, so 3 non-bonding domains. So 1, 2, 3, and then here's our 2 bonding domains. And if we cover up those lone pairs, now our molecule just looks like a straight line. So even though it's in the trigonal bipyramidal family, the actual shape that we see, the real life shape, looks like a linear molecule. So that's the name of this shape. So we could have linear if we had just AX2, or we can have a linear molecule if we have AX2E3. The bond angles for a linear molecule we already saw were 180 degrees apart. So now we're measuring the bond angle between our 2 axial fluorine atoms in this case. And those are 180 degrees apart. Moving on to our last major shape family, SF6 is going to be our example molecule to start. We're going to have sulfur as our central atom, and we're going to have 6 fluorine atoms surrounding it. And our fluorines will all have a complete octet if you were to calculate the total number of valence electrons you need to place. Number of electron domains around the central atom, we're going to have 6 bonding domains, so 1, 2, 3, 4, 5, 6. Our VSEPR class here is going to be AX6, and our electron geometry for the AX6 family is called octahedral. The molecular geometry or shape for SF6 is also called octahedral. And our bond angles are all 90 degrees apart. Now let's replace one of our bonding domains with a non-bonding domain. We're going to use BRF5 as an example molecule. And all the bonding domains are equal in an octahedral molecule, unlike with a trigonal bipyramidal where we replaced the equatorial positions. Since the bond angles are all 90 degrees apart, it really doesn't matter which one we replace. So we're going to have our bromine surrounded by 5 fluorines, and we can just choose any position we want to replace with a non-bonding domain or a lone pair, completing the outer octets on our fluorines, making sure they have 8 valence electrons, and then we're going to have 1 lone pair of electrons on our bromine atom. So our electron domains for this family, we have 1, 2, 3, 4, 5 bonding, and then 1 lone pair, so 1 non-bonding, total of 6 electron domains. How we represent molecules that fall into this VSEPR class are they would be AX5, E1 or AX5E. And when we replace one of our bonding domains to the non-bonding domain, our shape changes a little bit from octahedral, and it takes on a square pyramid type shape or square pyramidal. Now we have 1 lone pair that's pushing down slightly, shrinking those bond angles a little bit. So our bond angles are going to be slightly less than the perfect 90 degrees. For example, if we have a fluorine, bromine, fluorine bond that we measured, it would be a little bit less than 90. And the very last shape that we're going to study here is if we take 2 different bonding domains from our octahedral shape and replace them with non-bonding domains. So XeF4 is our example. We're going to have xenon in the middle, surrounded by 4 fluorine atoms. And the only rule here is the 2 Non-bonding domains are going to be opposite one another. So if we complete our outer octets to place all of our electrons, where we put our first non-bonding domain, we'll put that one in this molecule as well that was on the top. And where our second lone pair is going to go is on the bottom, directly opposite of that first lone pair. Remember, electrons have repulsions and they want to space themselves out as much as they can. And those two are exactly opposite one another, and therefore that creates symmetry in the molecule and lowers the energy. Our number of non-bonding, or our total electron domains, is going to be 6. We're going to have 4 bonding domains around our central atom and 2 lone pairs or non-bonding domains. The class here would be AX4, E2 for this shape. And now those 4 fluorine atoms that we're left with, they actually lie within a plane. You could think about them as being planar, where the lone pairs are sticking straight up from the paper and straight down. And so since they're planar, this is a planar molecule we're left with, and it's in the shape of a square, the actual molecular geometry is called square planar. And even though we have 2 lone pairs, they kind of cancel each other out. And now we're left with perfect 90-degree bond angles between the atoms within the plane. So our bond angles for square planar are 90 degrees. This is the last one within our octahedral family and the final shape that we'll study in this class. Once we can draw Lewis structures and use VSEPR to predict the shapes and the bond angles, we can determine if a molecule is polar or nonpolar. Molecule polarity predicts intermolecular forces between molecules, which predicts things like boiling points, melting points. It can determine if something is a solid or a liquid or a gas. So it's very useful to be able to determine if a molecule is polar or nonpolar. Polar covalent bonds we saw connected 2 atoms that had 2 different electronegativities. So for example, we saw if we had hydrogen bonded to chlorine in the molecule HCl, we could say that hydrogen has a less electronegativity than chlorine. So the atoms within the bond the electrons within the bond were not shared equally. They were pulled greater towards the chlorine atom because it was more electronegative. Our trend for electronegativity increased going up a family and increased from left to right. We used partial charges to represent the difference in electronegativity between the atoms. We would draw a partial positive charge on the more electropositive atom, which would be hydrogen, and we would draw a partial negative charge on the more electronegative atom, which would be chlorine. Recall this symbol is lowercase Greek delta, and it means partial. It kind of looks like an unfinished sideways infinity sign. A polar molecule will have a separation of charge. In order to determine if a molecule is polar or not, we have to consider the overall molecular structure or the VSEPR shape as well. Because sometimes if we have outer atoms that are the same and the molecule is completely symmetrical, those polar bonds can cancel one another out. Things that will usually lead to a molecule being polar are having different outer atoms, or where all the outer atoms are not the same, and usually electron lone pairs on the central atom, if the molecule is not symmetrical, will also create a polar molecule. Nonpolar molecules have no charge separation. Typically, they're going to be very symmetrical. Most of the shapes that we learned, as long as all outer atoms are identical, will be nonpolar. Let's consider 2 molecules, CH4 and CHCl3. CH4 we drew 4 hydrogens around our central atom, and we learned that the VSEPR class for this was called AX4, and it was a tetrahedral shape. And in an AX4 molecule, all of the hydrogen atoms are identical. So they all have the same electronegativity. Therefore, they are canceling one another out in this shape because the molecule is completely symmetrical. A molecule like CH4 overall is going to be classified as being nonpolar. We can think of bonds as vectors. And if the vectors, which have a magnitude and a direction, all pull in opposite directions and equally cancel each other out because the magnitudes are the same and the directions are opposite, that leads to an overall nonpolar shape. There are certain ways that our vectors will not cancel, which are often referred to, the vectors are often referred to as dipoles. And if we have a net dipole left over, that means that the poles aren't canceling, so the overall molecule will be polar. CHCl3 also falls within the AX4 family. Therefore, the shape is also tetrahedral. But now we have outer atoms that are not all the same electronegativity. Hydrogen is a little bit more electropositive. Chlorines are all really electronegative when we look at our trend. Therefore, the pull of the chlorine atoms is going to win. And that leads to an overall net dipole pointing in the down directions toward those chlorine atoms. This is called a dipole arrow. It's the same thing as writing the partial positive and partial negative charges. The arrow has a cross near where it would be partially positive, and it points towards the more negative side. So now our vectors are not all going to cancel because they're not all the same magnitude because of having this different hydrogen atom, even though the shape is overall symmetrical. So one way that you can have a polar molecule is by changing one of the outer atoms, and that gets rid of the symmetry, and therefore there will be a net dipole and the molecule will be polar. Another thing to look for is lone pairs of electrons on the central atom. Usually, lone pairs of electrons will lead to vectors that do not cancel, and therefore those dipole arrows will add up and give an overall net dipole moment, which means the molecule will be polar. So water and ammonia are two good examples of this. Water, if we draw our Lewis structure, we saw had two lone pairs of electrons on the central atom, and so the VSEPR class was AX2E2, and this was a bent shape. By having those two lone pairs, they do not cancel each other out, and the lone pairs pull at a different strength than the bonding pairs do. So we can see that the overall net direction of the dipole is towards those lone pairs. Therefore, water is a polar molecule. Ammonia, or NH3, if we draw its Lewis structure, we saw that we had nitrogen surrounded by 3 hydrogens. And on our nitrogen atom, we have 1 lone pair of electrons. Our molecular geometry was AX3E, and this was called Trigonal pyramidal. And notice our overall net direction of our dipole, due to that unsymmetrical lone pair of electrons, is pointing up because that's where those lone pairs, so that's going to be the more electronegative side of the molecule. You could think about there being a partial negative sign next to where those lone pairs of electrons are. And you could think of it being more partially positive down by where the hydrogen atoms are. So overall, there's non-cancellation, therefore there is a net dipole in the direction of those lone pairs. So both of those molecules, we would say, are polar. There are only 2 shapes that we saw that will actually have lone pairs of electrons, but the molecules will be nonpolar as long as the outer atoms surrounding are identical. So X is the same outer atom. Lone pairs of electrons live right here. So 2 electrons here, 2 here, 2 here. All 3 of these lone pairs on the left lived within the same plane. This shape was AX2E3, where 3 of our equatorial bonding domains was replaced with non-bonding domains. Our shape here was a linear molecule. That was in our AX5 family. Since all lone pairs are in the same plane, and they're all exactly 120 degrees apart, they essentially cancel each other because the dipoles are all pulling in a symmetrical fashion. The 2 other atoms are in the axial plane, and they're pulling in equal and opposite directions as long as their electronegativities are the same. So overall, this ends up being a nonpolar molecule. On the right-hand side, one of the last shapes that we saw, we would have lone pairs of electrons above and below the central atom, and all four of the bonding domains lied within the same plane. So as long as they're the same, those two non-bonding domains, or those two lone pairs of electrons, are pulling in equal and opposite directions, and that symmetry allows them to cancel each other out because they're perfectly 180 degrees apart. This shape was AX4, E2, and this was square planar. And if we see this where all outer atoms are the same, then there will be cancellation of those dipoles, and they are all pulling in equal and opposite in directions, so the overall molecule will be nonpolar. These two are the only examples where there are actually lone pairs on the central atom that they can cancel each other out and not leave a net dipole moment. So notice how symmetrical both of these molecules are. That great amount of symmetry is something to look for that will typically be an indicator of a nonpolar molecule. How we determine if a molecule is polar or nonpolar is first we draw the Lewis structure, then we determine the VSEPR class or the shape, and from there we analyze if it's a symmetrical shape or a non-symmetrical shape. So PCl5 and BrF5. PCl5, we have phosphorus surrounded by 5 chlorine atoms. All of our chlorine atoms are going to have a complete octet. We don't really need this part to determine the shape, but when we're calculating our valence electrons and practicing drawing Lewis structures, it's important to account for all of the valence electrons. Our shape is going to be from AX5 family, and this is trigonal, bipyramidal. We have 5 electron domains around our central atom. They're all bonding domains, and we've got our 90 degree and 120 degree bond angles between the axial and the equatorial positions. And this shape is very symmetrical. We have all of our outer atoms as chlorine, so they're all the same. Therefore, they're all pulling with the same want towards the electrons within the covalent bond. So overall, this is going to be a nonpolar molecule. With BrF5, if we compare that, we're going to have bromine in the central, and we're going to have 5 fluorine atoms surrounding it. All of our fluorine atoms will have a complete octet. And we're going to have 1 lone pair of electrons on our central atom. Our VSEPR class is going to be AX5E1, and the shape is called square pyramidal. Notice that we don't have symmetry in this molecule. We don't have 2 lone pairs of electrons pulling opposite of one another because of that pyramidal shape that was derived when we replaced only one of the bonding pairs with a non-bonding pair. So overall, this is a pretty non-symmetrical shape. And if we have a non-symmetrical shape, this leads to the molecule being polar overall. So most times when you have a lone pair of electrons replacing a bonding pair, it's going to lead to a polar molecule. The only case where it won't is if you have that symmetry and you have multiple lone pairs of electrons that could possibly cancel each other out. Let's try another example. Determine if the following molecules are polar or nonpolar. KrF2 and PH3. First we have to draw the Lewis structures. We're going to have krypton in the center, surrounded by 2 fluorines. The 2 fluorines are going to be above and below, or in the axial positions. And on our krypton, there's actually going to be 3 lone pairs of electrons within the equatorial positions. Our shape is from the AX2E3 family, and it will be a linear molecule where the fluorine-krypton-fluorine bond angles are 180 degrees apart. This is a circumstance where we have lone pairs, but because they're in their own plane and they're all essentially trigonal planar to one another, those lone pairs are canceling each other out within that equatorial plane. The axial positions are also pulling in equal and opposite directions because both of the fluorines have the exact same electronegativity because they're the same atom. So here we have an example where there's great symmetry within the molecule. It's highly symmetrical. Therefore, it's a nonpolar molecule. pH3 is our last example. If we draw the Lewis structure for pH3, we'll have phosphorus in the middle. Hydrogen can't be a central atom. We'll have 8 electrons to place. So that means there's going to have to be one lone pair on our phosphorus atom. Our VSEPR class will be AX3E, and this is going to be a trigonal pyramidal shape. Here we have a lone pair of electrons, which is not being canceled out by another lone pair of electrons, so we have a non-symmetrical molecule. Therefore, the overall molecule will be polar, meaning it has a net dipole moment, pointing in this direction overall. The partially positive or more positive hydrogens, and then the partially negative lone pair of electrons, which is not tied up in a covalent bond. You also have a handout that is a flowchart you can follow along while you're practicing to determine if a molecule is polar or nonpolar, and it gives you some leading questions to ask yourself. But overall, you're looking for symmetry and you're looking for lone pairs of electrons.